Thank you very much for the invitation. I enjoyed the visit, and this place is as beautiful as Iowa. It's snow and cold. And yeah, so I'm honored to give the last talk here. So I'm sorry, I changed my topic. I gave Professor Kim title and abstract in October. I didn't know what's the topic of other people, and once I'm here, I found that people before me already talked about the chemotaxis. So I changed my mind to talk about the chemotaxis instead. I hope you don't mind. So I started to work on chemotaxis model a couple of years ago. I worked with people who work in math biology, so I learned with them about the subject. And as I went through the lecture notes, Professor Miruma already talked about the chemotaxis model on Tuesday. So I will...
Just introduction, no mathematics.
So I will refer the introduction to that lecture, Tuesday lecture. So you already been exposed to the chemotaxis model and the phenomena. And there are beautiful results of pattern formation of chemotaxis. So I'm going to talk about what I did in this field with my collaborator. It's analytic result on traveling front mostly, and well postness, finite time blow up, and you'll see. So this is the outline, and so the phenomena of chemotaxis is the phenomena of cell attracted or repel the chemical. So the chemical can be food, or can be poison, or can be anything you can think of, nutrition. And the movement of the cell, it was observed, it is attracted to the gradient of the chemical concentrate. So this particular phenomena is called chemotaxis. And you can find chemotaxis phenomena in a lot of biological application, food finding, avoid poison, development and wound healing, immune response, cancer, metastasis, and so on and so on. And this is an observation of traveling bands in the chemotaxis phenomena. That's the result of 70. And so take the example of cancer metastasis. And when you, so why is cancer so hard to heal? The reason is because when there is a cancer cell in your system, and the cancer cell and the normal cell is attracted to the cancer cell, so the cancer cell will grow, and and also this kind of grow will get into your blood system. So once this cancer cell get into your blood system, it is very hard to get rid of. So this is a typical chemotaxis phenomena. So once you have a cancer cell, so their nutrition and attracted to each other, and while this thing attract to each other, the cancer cell grow in the body. So it is that's the mechanism. It's very hard to heal that thing. So the model, as introduced on Tuesday by Professor Mirara, this is the model I'm considering the killer sequel there's the two components. This is simplest kind. The two components. One is the cell density. The other is the chemical concentration. And as you can see that there are several functions here. It is the chemotaxis potential function, and if this is different, then you have a different equation describing different phenomena. So in the Tuesday lecture, Professor Mirora described 4 such function. I'm studying one of it. So this is the log of C, the log function. And this G is the kinetics. It just describes the interaction between the chemical and the cell. This kappa in here is a constant, and the function is in here. So this kappa can be positive or negative, and if this kappa is positive, then you have attractive chemotaxis. If it's negative, you have repulsive. And depending on the sign of this function, you may have the chemical can grow or it can decay while this happens. So this is the basic model, and when you really study the model, you will have to focus on specific situation. In the past, there are 2 major limiting cases being considered for the theoretic study. One is that you're assuming that the relaxation time is 0, so the chemical is in equilibrium to begin with. So you have this parabolic elliptic system. And for this parabolic elliptic system, there are a lot of results. In fact, in the past years, there are many, many results on this direction about existence and blow-up of solution, behavior of solution. So I did not list them all. You can see the reference and the reference in here. This major part of work was devoted to this parabolic elliptic system. So the other limit is that you could assume that, depending on the situation, you could assume that the chemical diffusion rate is 0. If that is the case, then you have this parabolic equation and this rate equation. And there are some results along this direction. Although this list is long, but the result along this direction is much less than the previous one. So this is just some new result, and also the thing I know. The previous system was studied more, and this is like a new one. So you can see some of the references, existing references, and also my work after I collaborated with my collaborator. So we did. So I will talk about what we did in this work. We studied the traveling front stability of rigorous stability traveling front and well-posedness. And also in this work we studied the well-posedness of the problem 1D with large data. And this work is the result that we convert our result back to the original system. And there are some recent development along this direction. This is my postdoctor. Hansen is one. He just graduated from Indiana, and he was at Iowa last fall. We did something there. And this involves the solution of chemotaxis in 3 dimensions. This is in 3-dimensional space, bounded domain, Newman boundary condition, and studied intermediate solution. That means the solution, the initial data doesn't have to be small in the space we work on. For example, H2, we only need the energy to be small, L2 norm to be small. H2 norm is bounded, it does not need to be small. This is the intermediate value. This is the term David Hoff worked on, invented this term. And in this work, we did well-postness, and in this work, we did the well-postness to a chemotaxis model, including rotation, tumbling, rotation, so there's a rotation. So the model was developed by Xue Chuan and her advisor, Asmer. Yeah, this one. This is interesting. This is a 2D problem. So this ongoing project. And so I'm going to go back to talk about what I did to some of the work, And the thing is, the case is, we studied the case as I mentioned. So the first case is that diffusion of the cell is positive, diffusion of the chemical is 0. And so we do have dynamics of chemical. And the chemotaxis function, this potential is log, and this G is minus alpha UC. So this means that the chemical is decreasing while this happens. This is negative. So you can think of this as food. It's being consumed in this process. This is a minus, and this is minus. This is a plus. This kappa is positive here. This is a minus. And this is a log. So the approach we adopt is to make a change of variable in the system. If we made a change of variable of this sort, and then take a derivative of second equation, we arrive at such a system of conservation law. It's a viscous conservation law. So the key step is the change variable here. And of course, this solely rely on that chemotaxis function is a logarithm function. Yeah. So after this change variable, the original system becomes such a quasilinear conservation law with physical viscosity. And we consider in one of the work, we consider the Cauchy problem. And in this work, we did study the Blowup criterion and local existence. And it turns out that the Blowup criterion, it is consistent with the phenomena that the bacteria is driven by the gradient of chemical. And as t goes to infinity, in this case, we will have a steady state as asymptotic behavior. So these are the blow-up criterion we just mentioned. So the solution is either global solution, or if it blows up in a finite time, it must blows up in this form. And this V is the gradient of C. So it's a gradient of a chemical reaction. And I will skip the proof of this local existence. And this part is the asymptotic behavior if the solution is close to a constant state and as t goes to infinity, and if the perturbation is small, and then as t goes to infinity, the global solution exists and also goes to that constant state. And for the initial boundary value problem, there are several previous work as I mentioned here. So this is one of the, we did this work, and there's other previous work, and this is also previous work. I mentioned that, so this paper worked on the original system, and this paper, we work on the transformed system. This is the original system. Now we're going to talk about the traveling wave, traveling front, the existence and stability. So as we know that the traveling band, traveling front phenomena was already observed and modeled. And in this paper, we are going to study the existence and the stability of the traveling wave to the Killer-Segal model, but in the transformed system. So this system was transformed from the Killer-Segal model, the very first one. So we transformed this system into that pair of viscous conservation law. And in that system, I took this D1 to be epsilon. This one is epsilon. And this tau is 1. So with this, with the same change variable, this is the change variable. With the same change variable, and we got to this pair of viscous conservation. This is for 1D, and but this transformation works for multi-D also. So our work is on 1D. So the traveling front result is on 1D. And so this system, this viscous conservation law, you can study the traveling wave yesterday. The speaker already talked about traveling wave. So it's a steadily propagated wave maintaining the same shape. And so we study this kind of wave. And if we look for this kind of solution substituted into the equation, we get a pair of ordinary differential equations. With the left and the right state, they are different. So it's a front. It's not a pulse. Because we had a pair of conservation laws, so the left and right state, they satisfy the Rankin-Lagrange condition. I think Baye, she talked about the shock wave earlier. So this is the shock wave condition that the left and right state, they must satisfy. And in order for such left and right state to be connected as a viscous profile, the speed must satisfy the what we call the entropy condition. If this entropy condition is satisfied, and then this is a necessary condition, then the ODE could have connection. And we are considering, so because that's a system of conservation law, there are two characteristic family of solutions. So we are considering the second characteristic family, shock, viscous shock. And this theorem is about the existence of such a wave. So we said that if the Rankin-Lagrange condition satisfied, entropy condition satisfied, and epsilon small, epsilon is the viscous of second equation, then there is a monotone shock profile. which is unique up to translation. So this monotone shock profile in U is decreasing, in V it's increasing. So such wave does exist. And in this existence proof, we use the phase plane analysis. And this proof has nothing to do with the closeness of the two states. So it is true for any two states that satisfies the Rankine-Lagrangian condition and the entropy condition. And so it turns out that if you drew the Nauck line of that two ODEs, so we had a 2 second order ODE because they are conservation law, so you can integrate at the end, you get a pair of first order ODE. So this one you can integrate, this one you integrate, so you're going to have a first order, and so that you can use a phase plane. So it turns out that this is the Nauck line, this is another Nauck line, and the flow of that ODE all flow in here, and this point is what's this? This is a saddle point, and that is a stable node. So we proved that the unstable manifold of this saddle lies inside here. Basically, we say the slope of this is between the slope of this and the slope of that, so that this unstable manifold get into this region, and there is no way it can get out. And there is a stable node here, and this trajectory cannot go around inside. Cannot be oscillatory because it's a monotone. Yeah, so it's monotone. You see, it's in the fourth quadrant. So the only way it can go is to here. The Bangari-Bendixson theorem says. So this gives you the proof of that existence of a traveling wave. And the next step, we are going to explore the stability of such wave. And by stability, we mean that, so for this capital U and that capital V, they are the solution, the traveling wave solution we just obtained. And now we go back to the Cauchy problem. We consider the Cauchy problem with the initial data U0, V0. Let's say the difference between U0 and a capital U and the difference between the V0 and the capital V, they are not so big. So it's a small perturbation. And then we say that if this is small perturbation, I will talk about this later. This is the antiderivative of perturbation. So then the Cauchy problem has a global solution if it's away from zero initially, later it's away from zero. And so the solution will be, the difference will be in this class for all t. And as t goes to infinity, the difference between the Cauchy problem solution and the traveling wave solution is zero. So this is the problem we are talking about. So here is the system of equations, and then we have a pair of initial data, U0, V0. And the U0 is a small perturbation of traveling wave. And V0 is a small perturbation of that traveling wave. And now we consider this Cauchy problem. And we can prove that the Cauchy problem solution exists. And as t goes to infinity, the Cauchy problem solution goes to the traveling wave solution pointwisely. So this is the meaning of the stability we are talking about. That's a traveling wave, and this is the this is the stability result. And the remark about the stability result is that our stability, our nonlinear stability, as you can see, that is a very, very strong result. We ask that the solution to, we proved that the difference, the supreme norm of the difference as t goes to infinity goes to 0. Such result hold regardless of the wave amplitude. So in shock wave business, we call this the stress of the wave. So the difference between left state and right state. So this can be arbitrarily large. Both our existence and stability result, we don't have a restriction on the size of this. So this is more physical. Because in physics, in a lot of theoretical result, this must be small, as in the previous work and in the general case. But in physics, the wave stress, they are not small. So this kind of smallness or largeness is case by case. It's treated case by case. It's kind of rare that we can treat the large case. And it also depends on the system. So the physical system is just like that. So we can do this. The most general case, there is still no such result. In every such result, previous result, there's a restriction that this is small. And in the P system, gamma gas, I guess there's a result of large data. It depends on the product of the gamma -1 times initial data. Yeah, that is also a large, considered as large data result. In any case, this is just the case by case result. In this case, we can do this. So the setup of the problem is we consider so this is the initial data that's traveling wave. We consider the difference, and we consider the case that this difference is along this direction. So it's a special case. And then the general case is not solved yet. And the previous result, a lot of result is along this direction. So this difference is along this direction. If the difference is along this direction, and so this serves as a shift. So if we shift the traveling wave this much, that is this much, and then we can calculate the difference of this Cauchy problem and the shifted traveling wave. And this turns out the difference is 0. It's 0 here, it's 0 here, after shift. And so this antiderivative is 0 at both plus or minus infinity. Did we introduce? Yeah, we introduced the antiderivative. So we introduced the antiderivative because the equation has conservation law. So we would like to work on the antiderivative to take advantage of the regularity of antiderivative. Right? Antiderivative is more regular than derivative. And so after that shift, you can see this. And this psi and phi, they are 0 at plus minus infinity. And so we will assume the translation is 0 for simplicity of notation. After that, we'll consider this data and that antiderivative. So the antiderivative, if you plug it into the equation, they will satisfy these two equations after integration. So here is the antiderivative we are working on. here. And we plug this into the equation here. You know that U is UV is a solution of this problem. Capital U, capital V, traveling wave, they are also solution of the problem. And then you make the difference. You get and you integrate. You get the equation for the antiderivative. So now we are looking at the antiderivative. The equation satisfied by the antiderivative of the perturbation. And we work on this space. This is our space, capital X. And we are going to estimate solution in that space. So if we can prove the a priori estimate that, you know, this capital N, if it is small to begin with, and as t goes to infinity, it is also small, and then we can prove the desired result. Okay, so we are going to make we are going to estimate. Oh, this is H2. Okay, so this is a subleft. If we can prove that, then we can conclude like this. And so this is a summary of the energy estimate where, so the initial data, initial antiderivative is in H2, even small. If the initial data is very small, the initial perturbation is small, that is the H2 norm. This is the H2 norm of the solution. This one. If this is small to begin with, then the Cauchy problem has a global solution in the space we just described. And this Cauchy problem solution satisfies the global estimate. This is true for any t. This is you know, you can see this H2 norm, and this is this weighted L2 norm, and this is like up to H3. And at the end, if we establish this, you see this is controlled by initial data. If we can establish this, and then by subleft embedding, we can prove that this goes to 0, and which is our small perturbation. So here, review one more time. Yeah, this phi sub x, psi sub x will be this difference. Okay, so that is the plan. And this is the equation they satisfied. So we are going to work on the energy estimate. Oh, I'm talking about how to get that. This is it. Okay, so then all we needed to do is to carry out the energy estimate step by step. Yeah, so the first step is the, oh, this is not the first step. This is again the detailed energy estimate. This is H2, and this is the weighted L2. And you see this diffusion will give you this good term, and that's diffusion. And then you have this initial data, and then you have this higher order term, the third order term, compared with the square term. And if we can prove the solution satisfy the priori estimate, it is small to begin with, and it will keep to be small, then this third order term will be under control. Now, now it's the L2 estimate. So in order to establish that, we just have to carry out this step by step. The first step is to establish the L2 estimate. The L2 estimate is, this is the L2 norm, and that's the weighted L2. And this is the diffusion from first equation. That's a diffusion from the second equation. And then you have the initial data, and this is the higher order term. I intentionally left this epsilon here, so you can see that the effect of that epsilon, if you want to see. For example, you can see if epsilon is 0, what happened. So this is the L2 estimate. So as you may know, when you do energy estimate, the key step will be the L2 estimate. If you can do L2 estimate, then you can do higher order estimate, because a higher order estimate is like the linearization of the nonlinear problem. So L2 estimate we did this way. So you remember we had two equations for phi and psi, and we are going to work on that, multiply the first and second. So we just do the necessary combination of these two. So it's kind of hard working and good luck. If you have good luck, then they can pair very well for you. If you don't have good luck, and you can work hard, but they still don't pair. And the thing is, for this physical system, and it works out well. They cooperated. So we did multiply the first equation by this, and the second equation by this, and add it together, and we were able to get to here this third order, and this is the traveling wave, so it doesn't matter. It's away from 0, and in here, the key thing is this. Okay, this one key term is this. This is the lowest order term. Yeah, you see, there's no other term that can save this. So all you can hope is that this is positive. So this delta look like this. This is all function of z. This is a traveling wave. This is a constant traveling wave. And as it turns out, the coefficient of this term is positive. And usually at this step, you will have to assume some assumption so that this is positive. For example, usually you assume the left state and the right state, they are very close. So the derivative of the traveling wave is very small. In that case, you can obtain some sign here, the good sign. But for this physical system, it turns out you don't need any condition. It is positive. So we can prove this without assuming the smallness, closeness of the two states. So that saved the day. This one has a good sign. And then this higher order doesn't matter. This third order doesn't matter. But then there's this term. This is the traveling wave. And it's also a bad sign. This is increasing. Remember, this is increasing. It's on the other side. So we had to estimate this term. And to estimate this term, you are going to do explore different linear combination of those two equations. And turns out if you do the different combination and use the fact that you already estimated some terms. So you combine this one and the previous one. You plug that in here. And make use of the fact that epsilon is small. And so you can combine this estimate all together. At the end, you get this one. So you see this good term in here, and this will, and this is good. And this one is also under control because of this estimate. You just do the estimate iteratively. So if you needed to do more, then you do more, explore more. So that is the L2 estimate, and then the higher order estimate, as I said before, it's easier. in fact, you don't need a smallness for this. You don't need the two state to be small, to be close to estimate H1. You only need that for L2 estimate. And but the H1 is like a standard. It's like L2. And you can work all the way up to H2. And at the end, you get to, well, let's review one more time. It's this one. Yeah. So at the end, you add this together, L2, H1, H2 together. You see, you have this good term. You may not use it, but it's here, and you have this, and then you use that Sobolev we just mentioned. Yeah, you use the Sobolev embedding. You can get this. You can get the bounded to begin with. This is small to begin with, and it's a small for all t. And at the end, you get this because you have this in the antiderivative in here. So this as t goes to infinity must goes to 0 because this is a uniformly continuous function in t. So you can prove this is uniformly continuous in t. So this indeed goes to 0. Because the integral from 0 to infinity is finite. And the integrand goes to 0 if it is uniformly continuous. It is, you can prove this uniformly continuous by the same argument. You did this 0t here, you can do t1, t2 here. Yeah, it will be uniformly continuous. And you can also argue from the point of view of the estimate, like H2 estimate you already obtained. So that concluded the energy estimate. So the higher order, the third order term, they can all be controlled by the second order term because you have uniform bound. And so, as we mentioned at the beginning, so all of this can be done because of that change variable that V equals gradient C over C minus gradient C over C. And so, of course, if we did a change variable, and then we are able to make use of the tool in nonlinear conservation law to prove existence and stability, and some of them are not available in the original system. So that's why we explore this. But the question is, if you did that change variable, you did get existence, you did get stability, what is the real meaning to the original in the original system? And we can, in this paper, we explored this transformation. Turns out that some of the traveling wave that looks very nice in this system does not make sense in the original system, but some of them they do make sense. So in that sense, so you can see the meaning of the work, you know. So it's, on the one hand, it's a mathematical piece of work. On the other hand, it may explain some of the phenomena. And this numerical simulation was performed in the transformed system, the quasilinear conservation law. So you have, we just started with small, actually this is not a small, it's a large perturbation of traveling wave. Traveling wave look like this. If you give this traveling wave a perturbation, such as this, and you let t evolves, and you will see that this kind of perturbation will disappear. So this means that this traveling wave is very stable. So you can perturb it, and after a while, it recovers to itself. this is. Of course, in our analytic work, we did not prove the larger perturbation. We can, in the future, we can explore, larger perturbation. But the numerical said that even for larger perturbation, the perturbation is absorbed by the. So it's quite it's quite stable. So this is also the same result. This is the initial perturbation, and this is the evolution after some time. So it is, in this case, it is quite stable. Yeah. So I said it before, and the problem in this field, there are enormous amount of problem. If you change the potential function, you change the reaction function, and you can also consider the growth. I thought we are considering a problem with growth of the cell. So they all result in a very different PDE. If you do transformation or you don't do transformation, you add this, add that. So I find this field is very fascinating. There are a lot of work, and if you can do something, and you may feel very satisfied. So maybe some young people in here, you like to study this field from your own point of view. Different people will study from different point of view. Yeah. Thank you for your attention.